In section 6.13, they're bringing up the derivation of the near-Earth approximation of gravitational potential energy. And we've already seen this when we were calculating the work done by the Earth. Because the work done by the Earth is just going to be mg for the near-Earth approximation times, in the case we were looking at changes in energy, so it's going to be the change in height. The reason that we can use this is, one, of course, going back to using the near-Earth approximation of gravity F is equal to approximately mg near the Earth, and then we can calculate that U, which is equal to negative the work done, is going to be equal to mg, and actually this is delta U, mg delta y. Another way to look at it is if we go to this equation right here, and let me just plot this, U versus R. And so what we're doing is we're saying, okay, let's say that this right here is the radius of the Earth. So if we go ahead and blow this part of the graph up, what we see is that that part right there more or less just looks like a straight line. So this part here is more or less a straight line. And with potential energy, it's really only changes in the potential energy that matters, not the actual value itself. So what we can do is we can say, okay, well, we've got a straight line equation here. Let's just go ahead and, for simplicity, let's choose some point to be 0. And so our equation for U near the Earth versus height is just going to be that straight line. Again, we're free to choose wherever y equals 0 is. Usually you choose something simple like the starting height or the surface of the Earth or whatever. So then to calculate the potential at any given point, it's just going to be U equals mg y. And what we actually are really concerned with is the changes in height. And we can see that because now in our energy conservation, so if we're using our energy bar charts, we have K initial plus UG initial plus the work done. That's going to be equal to K final plus UG final. And so it's actually the difference between mgy initial and mgy final that gives us our changes in potential energy. In the next section, we actually look at the electrostatic potential energy, and this is really, the derivation is very similar to the derivation for U grav. What really matters here is this 1 over R dependence. The electrostatic force had that 1 over R squared dependence, and so what really happened here is that U, delta U was equal to negative W, which is the integral of F dot dr. And when we go ahead and do that, and we end up integrating dr over r, integral dr over r. Oops, I forget my minus sign. And that ends up being, I'm sorry, this is r squared. And this just ends up being a positive 1 over r. So that's where that r dependence is coming from. And now with the gravitational force, we had a purely attractive potential, but right here, depending on the relative signs of these two, we can have either have repulsive or attractive potentials. So if both of our charges are positive or negative, this has a positive value at all times, and that curve ends up looking like this for a repulsive force. In other words, the two charges are pushed apart. Whereas if one of the charges is positive and one of the charges is negative, we end up with a potential that looks exactly like the gravitational potential energy. This is an attractive force. Now you may remember back when we introduced the concepts of the potential energy, that we talked about the important properties, and one of the important properties was that for repulsive forces we have positive potential energy, and the attractive forces tend to have negative potential energy. So you may want to go back and look at some of those properties.